So hello everyone, this is chapter 9 of Chemical Structure and Reactivity. I'm your host Brunagit/Palladium, and it's an honor to have you here. And here's the shout out list. Feel free to leave a comment or leave me a message on Discord if you want to be added to the list. For those on the list, a heartfelt thanks is extended to all of you for helping support the series. Now, last lecture, albeit, was kind of a doozy, right? Now, what we mainly talked about was bonding within the elements. Now, to be honest, having 69 slides of just pure content just does not help to pass the time. But don't worry for now, because this chapter is just a bit more general than chapter 8, and also just uses some of its more broad ideas. So we first talked about electron configuration, and then we talked about this thing known as the effective nuclear charge. And then we talked about relativistic effects, and then we talked about ionization energies across the elements, and then we talked about the various oxidation states that elements can take on. After that, we talked about bonding through the various groups of the periodic table. So we talked about bonding like the alkali metals, the transition metals, etc. So that's what we mainly talked about last time. Now we have to talk about bonding between the elements. Now, I'm going to outline a few key points for this chapter that I expect you to understand. When different elements combine, we can expect a lot of structures to form. And if we want to understand how these structures form, look at valence orbital energies. When different elements combine, we can expect a bunch of structures to form. And understanding orbital energies and orbital sizes can affect these structures and how their formation works out. And in addition, understanding radius ratios can help us understand the many different structures that ionic solids can take on. So, in essence, when we're talking about radius ratios, we're just looking at trigonometry and how balls stack. That's basically it. And our third key point is that comparing some compound structures with structures of other compounds that are isoelectronic can help us gain a better understanding. So, first, I want to go over the effect of size mismatch between orbitals. So, since we're talking about bonding, between elements, when different elements combine, it's beneficial for us to consider, first off, the sizes of atomic orbitals. Now, at typical bond lengths, the strength of the bond that is formed between two atoms of the same element is stronger as the orbitals get smaller, which indicates a greater degree of overlap. So if we go back to chapter 2, we went over this thing known as the overlap integral, which is basically you take two wave functions for electrons, you multiply them, and you take the integral of that. Now, the greater the overlap integral, the stronger the overlap is going to be, and thus that bond is going to be stronger. So as you can see right here, this table shows group 1 bond strengths. So you can see with hydrogen gas, H2, this one shows that the bond energy is 436 kilojoules per mole. For Li2, it's only 100. Na, or sodium, is 71 if it forms a diatomic molecule. Diatomic hydrogen is much stronger than diatomic potassium, which is 50 kilojoules per mole if we're talking about bond strengths. And you can see, because we're just descending down this group, then overlap will be smaller, which means that the bond strengths will, of course, get smaller. Here's a general rule for you. If we have two valence orbitals with around the same energy, and if they combine, then smaller orbitals will yield a stronger bond. And in addition, as per the book, a reason for stronger bonds is that the repulsion from core electrons is lessened. There are two kinds of bonds that I will need you guys to know. So, sigma bonding and pi bonding. So, sigma bonding is just head-on-head overlap of atomic orbitals. Take, for example, diatomic hydrogen. Hydrogen has one electron in each 1s orbital. Each 1s orbital is also a sphere, so we only get head-on-head overlap in the H2 molecule. However, pi bonding involves side-to-side overlap. So that's basic sigma and pi bonding. So, one more extreme cases where we can consider the sizes of valence orbitals in bonding is the creation of bonding molecular orbitals, which are pi in nature, from the overlap of two p orbitals. Now, the table below shows the energy that's needed to break the pi bond formed in a molecule, which is broken by rotating the two halves of the molecule, since pi bonds are formed from side-to-side overlap. Because if we have that side-to-side overlap, right, if we try rotating those two halves, then that side-to-side overlap is broken. And that means that pi bonding won't occur. And as shown in the graph, there's a rapid fall off of energy needed to break the pi bond. As you can see, once we get to period 3 elements from period 2 elements. So you can look at this. So take, for example, the most simple alkene of all time, right? Ethene. So the barrier, if you want to break that pi bond, is 274 kilojoules per mole. Now, if you look at something like selene, which is basically just ethene, but all you do is just replace the carbon atoms with silicon, then that barrier for breaking that pi bond is only 105. So basically, what this shows is that, one, as we go down periods, multiple bonding is not preferred, and in period 2 elements, there's a tendency to form multiple bonds. So, I'll give you one example. Take, for example, something like nitrogen and phosphorus. So, nitrogen normally forms as N2 gas. So, in nitrogen gas, there's a triple bond. But if you take something like phosphorus, phosphorus doesn't form diatomic P2 molecules at room temperature. It normally forms in multiple allotropes. I'll take one example, which is white phosphorus. So, white phosphorus is super volatile. This thing explodes in air. In white phosphorus, the only thing that we can see is just single bonds in lone pairs. And that's because of the larger sizes of the phosphorus orbitals. And this is going to mean that we're not going to get that multiple bonding, because there'll be weaker pi bonding. Next, I want to talk about the various bond strengths of diatomics. So here's the graph right here. I suggest you guys take a picture of it. The diatomics bond strengths seem to peak at around 10 electrons per molecule, which is because if we consider that molecular orbital theory view, right, having 10 electrons in that second period diatomic will maximize the number of electrons in bonding orbitals while minimizing those electrons in anti-bonding orbitals. So I'm just going to break this down real quick. If we have 10 electrons, max bonding, minimum anti-bonding. More bonding equals stronger bond. So in molecules where there's a general energy match between valence orbitals, bonding, especially pi bonding, remains strong within that molecule. But if we take something like lithium fluoride or boron monofluoride, then energy mismatch will lead to a decrease in pi bonding. So, this raises a question as to why the bonds in boron monofluoride and lithium fluoride are still somewhat strong. And this is because there's an increasing bond polarity in these compounds, and that leads to an increase in bond strengths. So right here's the graph. So you can see something like lithium fluoride does not have any pi bonding, but it's still super strong, even in terms of bond strength. And of course, the strongest diatomic of them all is carbon monoxide, as it seems. So right here is another image, because this chapter is somewhat visual. So this is another image of various pi bonding orbitals. So this just formed from various elements bonding together. So you can see something like diatomic fluorine, or just a fluorine bonded to a fluorine, right? The pi electron density is kind of spread evenly throughout this pi bonding orbital. But if you take something like an oxygen molecule bonded to an oxygen atom, bonded to a fluorine atom, then you can see electron density is somewhat more polarized towards that fluorine atom. And you can keep going on until you reach a lithium-fluorine bond, which is, of course, highly polarized towards the fluorine atom. So, let's go back to molecular orbital theory and we'll look at the MO view again. So, that charge separation that is present in compounds like lithium fluoride is known as an ionic contribution to the bonding character of the molecule. So, if we look at the molecular orbital diagrams for both nitrogen gas and lithium fluoride, there's overall a net lowering of electron energy within nitrogen gas. However, if we take something like lithium fluoride and we look at that MO view, then there's only one electron, that 2s lithium electron, that is lowered in energy. And this lowering in energy will allow for that bond between fluorine and lithium to be formed. Now, if the molecular orbital in which that 2s electron ends up in has no contribution from that 2s orbital, then the transfer of the electron to the molecular orbital would be complete, making that bond fully ionic. So you can think of a fully ionic bond just being like a seamless transferring of electrons with no contribution from one of the orbitals. However, in these quote-unquote ionic bonds, there will always be some covalent contribution. We know that in high school chemistry, right? There's that view of ionic lattices being present, right? So in high school chemistry, we might have thought something like, oh, there's a full transfer of electrons between these cations and anions, and the attraction between them will form this ionic lattice. However, in these ionic lattices, remember, there are no true ionic bonds. So there's always going to be some electron density in between those ions, no matter what. So I want to talk more about lithium fluoride. So it requires around 6 electron volts if you want to break that bond between atoms in one molecule of lithium fluoride, which doesn't make sense at first. Now, if you look at the energies of these various orbitals, the energy difference between the 2s orbital of lithium and the 2p orbital of fluorine is around 15 electron volts from each other. So, someone might say that the dissociant energy would just be 15 electron volts instead of only 6 electron volts. But we're not considering that the orbital energies were of the neutral atoms and not the ions at hand. And once we quote-unquote donate an electron from the lithium atom to the fluorine atom, the energies of the electrons will all change to some degree. So that's just some more lithium fluoride talk. So we're going to go on from here. So next I want to talk about the classification of compounds. So attempting to classify some compound as ionic or covalent is honestly a massive oversimplification of what we've learned so far in this chapter, because seemingly ionic compounds, which some may think there's a complete charge transfer, can still have covalent contributions such as lithium fluoride. Now, what this means is that for seemingly ionic compounds in the lattice, there'll be some electron density in between the atoms, but nonetheless, there's still somewhat of a distinction between these covalent and ionic compounds, with each type of them having different properties. So now, we still end up with the properties of these quote-unquote different types of compounds. So, the properties that are most associated with these quote-unquote ionic compounds are an ability to be easily soluble in water, a larger melting and boiling point compared to covalent compounds, and ionic compounds can also conduct electricity if you can melt it or it's in solution, but not as a solid, which you can see with simple tests, such as just looking at if you can pass an electric current. For covalent compounds, we have lower melting and boiling points, a relative inability to conduct electricity compared to ionic compounds, and they're more soluble in non-polar solvents. So, if you know like some kind of organic solvents, right? Covalent compounds are more soluble in these non-polar organic solvents like benzene or carbon tetrachloride. And in addition, they often form these discrete molecular units in solids. So, those are just the various properties of these different kinds of compounds. Now, the next thing I want to do is I want to talk about orbital energy and bond type. So, most likely, the best way if you want to tell if a bond is more covalent or ionic is to see how closely matched are the energies of the valence orbitals. So, a large difference in the energies of valence orbital will make that compound more closely resemble the characteristics of an ionic compound. However, a smaller difference would match much more of a covalent compound's properties and bond character. But overall, bond characteristics are on a spectrum. I repeat, a spectrum from nonpolar covalent to ionic. So there's no kind of like barrier, no kind of like tipping point that we can use. So it's all just a spectrum. Now, we can use our knowledge to infer the character of the bonds in the compounds shown in the diagram that are right next to this block of text. Right here, we can just use our knowledge to figure out, the boiling point, the strength of intermolecular forces. So I won't get into all of that, but this is just what you can understand if you understand orbital energy differences. So let's go on. Next, I want to go over this thing known as the Van Arkel diagram. So in the 1940s, this was developed by Van Arkel and Keeler, and was later on improved in the 90s by Sproul. So in this diagram, we utilize two metrics: the average between orbital energies and the difference between orbital energies. And we simply plot them out on this kind of graph or spectrum so we can infer the kind of characteristic of the bond that's going to be present. So on the edges of the triangle, cesium is the most metallic element, diatomic fluorine is considered the most covalent compound, and cesium fluoride appears to be the most ionic compound. But here's the little fact I want you to know. I was kind of surprised at first that it would not be francium fluoride, but if I just look back at my knowledge from the last chapter, if we consider those relativistic effects, which amplify in heavier elements, it all makes sense. So right here is the Van Arkel diagram. As you can see, very great. Overall, I'd say it's good for classifying bond character. So you could look at something like lithium fluoride and say that it's more ionic in character if you're talking about the bond than lithium oxide. Next, I want to focus on the various structures that we have for different oxides. Right here is a big chart just showing you the oxides of various elements. And generally, some metals may form multiple oxides, so we just decided to choose the oxide that's considered the most stable. So we have stuff like lithium oxide here, magnesium oxide, gallium oxide. We have stuff like ozone, nitrogen dioxide, carbon dioxide, oxygen difluoride, stuff like that. And we can see right here, there's a kind of key here. So, oxides that are red have somewhat of an ionic lattice structure. Oxides that have this orange color are polymeric polar covalent structure, which is somewhat like in between of an ionic lattice and a molecular covalent structure, which is for these oxides that are yellow. So right here is just some information about the past chart. So generally, the oxides that have the largest orbital energy difference have the highest coordination number ratio, which is just simply the number of nearest neighbors for a single atom if we're considering some kind of lattice. For the compounds that have a lower difference in orbital energy, a lower coordination number ratio is observed, and the structure is mainly discrete molecules. However, In between that kind of ionic lattice and discrete molecular view, there's some intermediate structures that can be formed, like nets, sheets, and chains. And it's in between those ionic and molecular covalent structure regions. So like around this kind of orangish area, you'd find stuff like chains, nets, like that. So next I want to go over some different structures. So in the last chapter, we talked about how the structures for certain compounds can be derived using models such as the antibonding and the lone pair repulsion effect. So basically, when we're talking about antibonding and the lone pair repulsion effect, we're just talking about, at least in the last chapter, we asked a question about why compared to like fourth period, fifth period, third period elements, second period elements don't form metallic structures and instead form discrete molecules. When looking at the difference in orbital energies can act as a general guide, remember that this is chemistry. And in chemistry, exceptions are everywhere. And we must learn some new knowledge in order to rationalize why these exceptions are the way they are. So, take for example gold 1 iodide, so AuI right here. It has a lower coordination number than copper 2 iodide, even though the orbital energy difference is greater in gold 1 iodide. So we need some kind of new way to determine the various structures of compounds. So here's a quick little concept. So if we can't use the difference in orbital energies to figure out the structures that various compounds take on, then what are we supposed to do? Now, here's a little thought from Lil Jimmy. He says, what if we go back to that last chapter and think about how spheres stack together? I knew that the last chapter was bonding in the elements, but honestly, let's try. So, thanks Lil Jimmy for that thought. So, we can use the radius ratio of the elements present in compounds to predict the coordination number. But so far, I don't know how to determine it. And Little Jimmy also says, what if we try using the Greek letter rho as the symbol for the ratio? And yeah, we can do that. So I was thinking of using trigonometry and the angle between the center of one atom and the center of another atom to derive that radius ratio. It turns out, with some simple diagrams, we can say that the sine of alpha is just that kind of angle between, you can see right here in this diagram, it's kind of that angle between this sphere and this sphere, right? And we can say that the sine of A is equal to R, big R, which the radius of that blue sphere, over R plus R. So big R plus little r. And alpha is the angle right here. And you can understand that once you look back at the definition of what the sine function is. So if we go back to the sine function, right? SOHCAHTOA, so sine is equal to the opposite over the hypotenuse. So big R is going to be our opposite, and this side is the hypotenuse, which is just big R plus R. Now, if we use some simple algebra, we can define the radius ratio, which is defined as rho is equal to small r over big R. And now the radius ratio is equal to 1 over sine alpha minus 1. Now we can determine the limiting radius ratio for a certain arrangement, so just the minimum radius ratio. And in addition, if you want to determine the radius ratio for a certain arrangement with some kind of coordination number, then here's the equation right here. Rho coordination number, which denotes Cn, is equal to the square root of 12 over 12 minus the coordination number minus 1. So for some lattice made out of compound that has the formula ANBM, the coordination numbers may be different as N and M are not in that 1-to-1 ratio. So therefore we can just say the coordination number of B is equal to N over M times the coordination number of A. So that's just something that we can clear up if we have that 1-to-1 ratio just not present. So take for example, we're using the radius ratio in practice, NaCl. So this has a radius ratio of around 0.564 if we use our knowledge of ion sizes. So therefore, This means that the coordination numbers for both sodium and chlorine are the same, which is 6, as you can see here. And in fact, if you look at the lattice of sodium chloride, you can just see how the coordination number is 6 for both sodium and chloride. While using that radius ratio may seem all fun and games, there's a few issues with using it for various compounds in the periodic table. So, our first issue that we have is that it will be hard to determine the ionic radius of various elements. Because, think about this. There's no kind of clear boundary. Like, ions are not just spheres that you can stack onto each other. It's kind of a fuzzy boundary on which you can determine that size. And in addition, many other factors can affect the spacing of ions in a lattice, such as oxidation states. Now, our second issue is that there are a bunch of structures that we can have that have the same coordination numbers. And since the radius ratio only gives us the coordination numbers, we still can't figure out that exact structure if there are multiple with the same coordination number. So finally, while this approach of looking at how spheres stack may seem good for more ionic compounds, with a higher difference in orbital energy, we can use it for compounds with ones that have characteristics on that other end of the spectrum, so a lower difference in orbital energy. Now I want to talk about two not compounds per se, but structures that have lower coordination numbers. So these structures are known as zinc blende and wurtzite. So zinc blende is a structure that's based on one form of the mineral known as zinc sulfide. And this can be coupled with a different structure known as the wurtzite structure. So right here is the chart showing some various compounds that take on this zinc blende or wurtzite structure. Now, both structures of gallium arsenide and aluminum nitride can show similarities to the structure of diamond, which is made of carbon, an element in group 14. Now, since these compounds are made from the elements in group 13 and 15, we can say the structure is somewhat isoelectronic with the elements of group 14. That's something interesting to know. So this is what I mean by isoelectronic structures. Most of the compounds that are found to have zinc blende or wurtzite structures are isoelectronic with elements of group 14. However, we always have exceptions, such as beryllium oxide, which is predicted to take on that wurtzite structure, and it does. But if we look at something like magnesium oxide, it does not. However, overall, as shown in the graph that will appear soon, there's still somewhat of a general trend in orbital energy difference and the structure that these compounds can take up. So, right here, this is kind of a correlation between radius ratio and orbital energy difference and overall the structure that these elements will form. So you can see beryllium oxide, region for predicted CN6. It has a wurtzite structure, while magnesium oxide has a rock salt structure, even though they're in the same coordination number predicted of region. Now I want to talk about even more isoelectronic structures, and we can now say that if we have some kind of compound which is formed from a group 14 and group 16 element, it can be thought of isoelectronic to a compound made of group 15 elements only. So, take for example carbon monoxide. So it's a very deadly gas, and it's isoelectronic with nitrogen gas, which you can find out with using the complicated method of counting. So, other oxides of group 14 elements have more of an ionic character, and thus take up structures that have higher coordination numbers. And in addition, there are also some kind of smaller differences in orbital energy when you're pairing group 14 elements with heavier elements from group 16. So next I want to talk about these things known as Zintl phases. So this was studied by German inorganic chemist Eduard Zintl back in 1930s. So we get some more interesting compounds if we pair the heavier elements from groups 1 and 2 with the elements in the P block from groups 13 to 16. So in these compounds, the anions arrange themselves in such a way that the arrangement is like the elements in the group that have the same number of valence electrons in the anion. So That was kind of a mouthful, so I'm just going to put a simple explanation down on the bottom. So take for example, if we have anions in group 13, if we add one electron per anion, then in that Zintel phase, the anions will arrange themselves in such a way that it looks like it's a structure from group 14. Now I'll show you a few Zintel phases. So we have two compounds, so MgB2, so we're going to get B minus ions, and NiIN. So these indium ions are going to have a charge of -1. They show these Zintel phases, and by the way, boron and indium are both in group 13. And since one electron is added per anion, they arrange themselves in these carbon-like arrangements. So you can see in MgB2, the boron ions arrange themselves in this graphite kind of structure. But in NaIN, these indium anions kind of arrange themselves in this diamond tetrahedral structure. So that's something that shows, how interesting these Zintel phases are and just like the whack stuff that you get in like crystal chemistry. Next, we're going to look at group 15's isoelectronic structures. So we're going to look at two examples, so calcium disilicide, which is CaSi2, and K4Si4. So these silicon ions are going to have one electron added per anion. So thus we're going to get group 15 isoelectronic structures. So, for example, in calcium disilicide, these Si- ions kind of form sheets that are similar to the structure of arsenic, and these calcium cations are in between those sheets. And as for K4Si4, the Si- ions form in some kind of arrangement that is similar to that of P4, which is the unit that you'll find in like white phosphorus. So, although this chapter was a bit shorter than expected, we've looked at how broad trends in bonding between the elements of the periodic table can be explained with orbital energy, the effective nuclear charge, and orbital size. So chemistry is just all about how these bonds are formed and changed. In this next chapter, we're going to talk about how we can model reactions with, guess what, more molecular orbital theory. So there will be somewhat of a focus on organic reaction, and this will be drawing from your knowledge from chapter 5. Especially if we're talking about interactions between different orbitals, homolunar interactions will be important.